Now that we established the main idea that we'll need to make a domain restriction in order to define what the inverse trigonometric functions are, let's get into the details. So I have a graph of sine t in front of me, and I've only graphed the portion from 0 to 2 pi, but I'm able to copy and paste this so we can see a greater portion. So if I paste the curve again, I can paste it over here, and I can paste it over here to the left. And I have this stray pi that I have copied, so I think I'll go ahead and erase that. So there we have a reasonable picture of the graph, and what we're going to do is we're going to ask ourselves, what portion of the graph can we delete in order to create a one-to-one function? Now the answer to that question is actually a bit interesting. There's many different portions of the graph that you could delete in order to obtain a one-to-one function. So for example, if we deleted all of the graph except for the portion between 3 pi over 2 and this would be 2 pi plus pi over 2, so 5 pi over 2. If you ignored the rest of the graph, then this would be a picture of a one-to-one function. Any horizontal line that you draw only intersects the graph once in between 3 pi over 2, 3 pi over 2, and 5 pi over 2. Of course, outside of my vertical lines, there's other intersections, but again, we are deleting outside of these vertical lines that I've drawn between 3 pi over 2 and 5 pi over 2. And there are many other choices that can be made in order to create a one-to-one function, but the mathematics community has decided on a standard choice, a standard restricted domain, in order to define the inverse sine function. And it's not this one that I've drawn. The standard restricted domain, so let's go ahead and erase this, is between minus pi over 2 and pi over 2. So minus pi over 2 is here, and pi over 2 is here. So when we make this inverse trigonometric function of sine, we simply ignore everything here that I am erasing. And we only look at the part that is remaining. And I suppose if I erased everything that I don't need my vertical lines here. Let's write the conclusion of this definition, or this discussion, which is a definition. So we define the inverse of sine, which we'll write, let's write it with the independent variable x. So sine inverse of x is the inverse of sine of t with domain minus pi over 2, comma, pi over 2. So normally sine of t, if you just were focusing on sine of t and you said what is the domain of sine of t, then the answer would be all real numbers. We've established that you can put any value of t into sine of t. But for the purposes of defining the inverse, we have restricted the domain to be between minus pi over 2 and pi over 2. The consequence of this is that when you go to evaluate sine inverse of something, so let's say we wanted to evaluate sine inverse of 1. Then to evaluate this, we'll proceed much like we did with the example with the quadratic function a bit earlier. Let's see, right here. So we start by setting it equal to t, and we'll need to apply the domain restriction here. So I'll set it equal to t. I'll write what it means in terms of the original function. So that means that 1 equals sine of t, and t has to be between minus pi over 2 and pi over 2 because that's how we defined our domain restriction. And so at this point you have to think, what value of t between minus pi over 2 and pi over 2 gives me that sine of t is 1. If you thought about this for a moment, you would realize that t is pi over 2. So t equals pi over 2. And so sine inverse of 1 is pi over 2. Now, to be very clear here, it would not be enough if you did not put this domain restriction, because there are infinitely many t's for which sine of t is equal to 1. In fact, if you take pi over 2 and you add any increment of 2 pi, any integer increment of 2 pi, then you get another solution, because if you add some integer increment of 2 pi, you go one full revolution or some number of full revolutions around the unit circle. So for example, if you did not include this here, you would find that not only is pi over 2 a solution to sine t equals 1, but also 5 pi over 2, because 5 pi over 2 is pi over 2 plus 2 pi. So when you just write sine of t equals 1, there are infinitely many t's which satisfy this equation. However, when you specify that, in fact, let's see if I can erase this here, when your t is between minus pi over 2 and pi over 2, that makes it so that there's only one solution. And so while there are very many domain restrictions that we could have made to this graph, this is the commonly accepted standard domain restriction. And I also like to, when I define what the inverse trigonometric functions are, I like to state the domain restriction in terms of what it looks like on the unit circle. So our t values are allowed to be between minus pi over 2 and pi over 2. So on the unit circle, let's go ahead and draw a circle here. Let's go ahead and draw what angles this includes. So here's a unit circle. The angle down here is minus pi over 2 if you go, of course, clockwise instead of counterclockwise, and the angle up here is pi over 2. And so the restricted domain of the sine function in order to create the inverse sine function is this right half of the unit circle here. This is a good picture to have in your head, because let's imagine again we wanted to figure out what sine inverse of 1 is. Well, we set it equal to t, and we switch the inputs and outputs, and we see that 1 is sine of t with t between minus pi over 2 and pi over 2. So at this point, you can envision the unit circle and say, well, where is sine of t equal to 1 for t between minus pi over 2 and pi over 2? Well, you're asking yourself, at what point on the right half of the unit circle, because t has to be between minus pi over 2 and pi over 2, you have to be on the right half of the unit circle. For which angle do you have that sine of t is 1? And remember, sine of t, that's the y-coordinate. The y-coordinate is 1 up here at the top. So envisioning the portion of the unit circle that corresponds to the restricted domain will be, I would say, very useful when you go to evaluate inverse trigonometric functions. Now that we've defined sine inverse of t, let's define the inverse of tangent. So here I have a graph of tangent, and of course it repeats over and over again. I'll just sketch the repetition. I won't be too extremely careful in how I sketch it, but let's have a sketch nonetheless. And this obviously fails the horizontal line test, but if I delete these two curves that I just made, then it passes the horizontal line test. In fact, this is the domain restriction that we typically make for tangent of t. We take all of the t's between minus pi over 2 and pi over 2. Just like sine of t, with the exception that tangent of t is not defined at minus pi over 2 and pi over 2. And so we define tan inverse, the inverse of tangent. Let's use the independent variable x. This is the inverse of tan t, where t is between minus pi over 2 and pi over 2, and I'm just not going to include minus pi over 2 or positive pi over 2. I'm not going to write this because tangent of t is not defined at either minus pi over 2 or positive pi over 2. So tangent of t, we use almost the exact same domain restriction. I suppose I should probably put those words here, so with domain. So we use the exact same domain restriction almost as sine of t. So for example, if we wanted to figure out what is tan inverse of 1, well, we would set this equal to t, and we would switch the inputs and outputs and write what this means in terms of the original function. So this means that 1 equals tan t with t between minus pi over 2 and pi over 2. So you would be searching for some angle t between minus pi over 2 and pi over 2 such that tangent of that angle is 1. And again, it's useful to have a unit circle picture of the t's that satisfy t between minus pi over 2 and pi over 2. That is this right half of this unit circle. But do remember that in quadrant 4, it's the right half with the t values between 0 and minus pi over 2, not between 3 pi over 2 and 2 pi. In quadrant 4, when we define the inverse trigonometric functions, this is 0 and this here is minus pi over 2. Okay, so what value of t gives me that tangent of t is 1? Well, t equals pi over 4, because at t equals pi over 4, tangent of pi over 4 is equal to root 2 over 2 divided by root 2 over 2, which is 1. And pi over 4 is the only t value between minus pi over 2 and pi over 2 that gives me tan t equals 1. Again, to be clear, there are other t values outside of this range that give me tan t equals 1. You can check that tangent of 5 pi over 4 is also equal to 1. That's true. However, 5 pi over 4 is not between minus pi over 2 and pi over 2. And so tan inverse of 1 would be pi over 4. Let's finish up our definitions with what domain restriction we make to define the inverse of cosine of t. So the standard domain restriction to make for cosine of t is t values between 0 and pi. Of course, when we erase the rest of the graph here that's not between 0 and pi, we see we have a 1-to-1 function. And inverse cosine of t is going to be defined as the inverse of cosine t with this domain restriction. And so let's go ahead and write that. So cosine inverse of x is the inverse of cosine t with domain. And here we don't have to exclude the endpoints like we did with tangent, because cosine is indeed defined at both 0 and pi. So this domain restriction is a bit different than the domain restrictions we made for for sine of t and tangent of t. The part of the unit circle that 0 pi represents is the top half of the unit circle. So when you are envisioning the unit circle to solve some inverse cosine problem, you should be envisioning the top half of the unit circle, the t values between 0 and pi. Let's do an example. So let's say I wanted to figure out what is cosine inverse of negative root 2 over 2. So we'll do something very similar to what we have been doing. We'll set this equal to t, and we'll write what this means in terms of cosine. So this means that negative root 2 over 2 equals cosine t. And so I'm looking for a t such that cosine t is negative root 2 over 2, and I'm on the top half of the unit circle. That's going to occur in the second quadrant. Here our t is going to be 3 pi over 4. Again, I'll make the obligatory remark that there is a place in quadrant 3, 5 pi over 4, where cosine is also negative root 2 over 2, but that is not in our domain restriction. And so we would make the conclusion that cosine inverse of negative root 2 over 2 equals 3 pi over 4. Now that we've introduced the inverse sine, inverse tangent, and inverse cosine function, I want to make a couple remarks. The first is that there's an alternate notation that is used in some textbooks and in some other classes. For example, arc cosine of x, that's the same thing as cosine inverse of x. Sometimes you see that cosine inverse is called arc cosine. And similarly with tangent and sine. Arc sine is the same as sine inverse, arc tan is the same as tan inverse. Also, it's useful to keep in mind that whenever you do cosine inverse or sine inverse or tan inverse of something, remember the output for all of these is an angle. It is very useful to keep this in mind as you go through various problems. So when you write cosine inverse of 1/2, you are, if you're trying to evaluate this by hand, you're looking for some angle t such that 1/2 is cosine t, and that angle has to be between 0 and pi. So keep in mind that there is this alternate notation, and also that the output of all of these inverse trigonometric functions will always be an angle.